So in this video, I'm just going to start talking a bit about copy IDs with volumes, in physical volumes in particular. So you might remember this slide that I showed a bit earlier in the video list where I started talking about detector construction or geometry in Geant4. So you might remember that from one single volume, we can make multiple logical volumes, and from those logical volumes that we can then place those logical volumes multiple times as multiple physical volumes, and we can then retrieve what volume we've got with a copy ID or volume ID number. So this is particularly advantageous or convenient if you've got, say, a pixelated detector, and if you just want to record all the energy being deposited in a certain pixel, then you can just record all the dose or energy being deposited in each separate volume with its own copy ID, and then at the end of the simulation you can just return the energy deposition. So let's just fire up our trusty old detector construction. So we've got our world volume and a water cube. So let's say we've got a pixelated detector, but let's just make it just simple blocks that are arranged in certain spacing. So let's say we've got a 3x3 array. Let's say make a pixelated detector 3x3. So let's make a 3x3 detector. So let's first decide how large we want to make our pixels. So let's just have them as since our box is 50 centimeters, let's have our volumes as 5x5, so 5 centimeter cubed. So let's just have our Geant4 double and have our detector size and put that to 5 centimeters, and we'll just copy this code here for our box. So what have we got here? Let's call this detector box and change this to detector box. Very imaginative. And let's just replace those dimensions. So it's all 5 centimeters. And for the log box, let's just call that log det for logical detector, and we'll have that as the detector box as the solid volume, and we'll just keep it with water for convenience. And let's just change this to log det box for the logical volume. So then comes slightly newer and tricky part. So if we've got a 3x3 pixelated detector array, then we need to tell simulation our spacing. So let's just say each volume is 10 centimeters apart from each other. So let's just go Geant4 double and pixel spacing X and put that as 10 centimeters, and then Geant4 spacing for the Y, let's have that as 10 centimeters also. So this would just be the spacing between the center of each cube that we place, which is 5 centimeters cubed. So if we wanted to just place a single volume, we could just do this method here that we've already got. I might just visualize it now, just for memory's sake. So is our, what did we call it? Already forgot. So log def, and we want that in the phantom, what have we called it? The log box for its mother volume for this detector, and zeros, and this copy ID, and this is checking for overlaps. And let's get some visualizations. Let's put this detector as red for danger. So I'll just put 100 for the color and name, log volume name. So just give it the logical volume name there, and let's make it solid because that's a bit more exciting. Let's just quickly compile that. See if there's any issues so far. So water was not declared in this volume. That's right, because this is the WotC version of the code. So let's just quickly make water again. So just water, all caps, and change that to water there, and compile. It's good. So let's just check our visualization. That's about right. So remember, got our meter cubed world on the outside, and this inner water cube is 50 centimeters cubed, and then this cube itself is 5 centimeters cubed. So looking good. So what we want to do is have an array of 3 by 3 volumes of this single pixel, as in with this single logical volume, we want to replicate it 9 times. So we've got our spacings for the X and the Y. So now all we need to do for this case is do a for loop in the X and the Y. So we're going to loop over the different X positions and the different Y positions. So let's get our first for loop. So int I, do I want to use a double? We'll use a, go for a double actually. And yeah, we'll go with the double. No, I changed my mind. Go for a int. So I was just thinking how to do the looping in the X and the Y. So let's have a variable called dx for detector X and initialize that to 0. We want dx, so the number of detectors placed in the X row to be 3 times, and we want plus, and I'm just gonna leave this down here. It's commented just to get out of the way for the moment. And we want, actually let's just start in the X first, then add the Y second. So let's put this in here. So we've got our logical detector defined. Now we're just going to place 3 logical volumes, and we just checked it with 1 single volume that it was all set up correctly. So let's just define our our detector X position. So let's call it detect X. Let's dx pos. I like that. So dx pos, and I'm just gonna have a simple spacing. I'm just gonna have it in the center of the world, as in the origin, and just place it from there. So let's just quickly visualize to try to demonstrate what I mean. So what I want to do is have 1, 2, 3, 1, 2, 3, 1, 2, 3. So for the X's in the for loop, I'm going between 0 and 3. So what I'm going to do is just go use the origin as the reference position and just start here and just do a shift. So let's go back to our detect construction, and let's let's actually have our, so we're going to start in the origin, and our pixel spacing in the X is pixel spacing, and let's times that by dx. So for every new spacing we can, for every new detector or pixel, we'll have a shift of 10 centimeters. And so we want the, since it's 3 by 3, we want to have the total spacing. So let's, I'm just thinking out loud how to do this the cleanest way. So let's also introduce a starting X position, or let's go start dx for start detector X, and we'll put that as actually so let's get the total range of the detector. So let's actually have Geant4 int and go number X. So let's go number dx for number detectors in the X and put that as 3, and also number of detectors in the Y, and sorry, number Y, and put that as 3 as well. So for our, we'll have a range of X dx, so range dx, and so we'll just put our number of dx, and we'll put the pixel spacing here. So if we just look at the numbers now, so we've got 3 and times by 30, and so this range of dx will just be in terms of the centers. So the furthest the pixel to the other furthest pixel, the center of the pixel. So this isn't say the leftmost pixel position to the rightmost pixel position. This is just the range that the centers of the pixels range over. So just to point that out, because sometimes with volumes it's important to specify whether you need to care about the center position or one of the edges, like one of the top or the bottom edges of a volume. So it's important to just to be sure you don't have to shift a volume by a half or something like that. So now that I've got my range, so let's have that as our starting position, so to speak. And so let's start that there. In fact, let's have that as negative. So we'll start in our negative 30. I'm just thinking out loud. So negative 30, then plus our spacing. So, oh wait, we want that to be half. So we start at minus 15, then plus shift by 10 each time. So I'm just going to quickly compile that, and oh wait, let's put our actual position in. So dx pos, and we want that in our X position now. So remember XYZ placement, and let's see if that compiles. I'm feeling a bit unconfident. So let's just compile that. And let's just quickly visualize. All right, so we were X and Y, so it's looking promising. so far. So actually, is that a bit shifted? Oh, okay, it's a bit of offset. So, oh yeah. So 15 minutes now. So I'm just going to pause and we'll continue on the next one so we don't get too long at once.